Okay, hello. My kids and my wife are out at, what are they doing? The book fair at school and like a bingo event. And I'm not going, so I'm going to see if I can get this video out to you guys while they're doing that. Hopefully, you'll see it a little earlier. Quiz is not tomorrow. I put out a remind and I put out an announcement on Canvas, so I hope you heard. But I am going to have the quiz Thursday. There's just no reason not to take another day. So we'll take another day. But anyway, let me just get into this. I guess I already did the two questions from the white sheet. There's an answer key. So I'm just going to do the problems from the yellow sheet as a video. And hopefully that's enough. If it's not enough, you can come see me tomorrow during, well, there's no advisory because it's Wednesday, but see me during lunch or after school and I'll be sure to help you more. Anyway, let's do number one, which says, ugh, sorry. Um, it says that the line that's tangent to a of x also hits the graph of a of x at another point. Find the coordinates of that other point. So we've had a problem like this before, but if you're not sure what the heck these even mean, I'll kind of sketch out what's going on. We know that we've got a of x, which is some cubic function, so it probably comes up, goes down, and then continues up, up, up again. And we're trying to find the tangent line at -1, so maybe that's here. And the tangent line at -1 would probably go like this. And you can see that, yes, it's tangent at that point of tangency, but if you continue on forever, then we do see that that tangent line hits the graph one more time. So that's what we're trying to find, is we're trying to find the coordinates of this point right here. Those coordinates will be the answer to the question. And how do we get there? Well, probably the first thing we should do is actually find the coordinates of our point of tangency. We know that x is -1, so we already know that. To find the y coordinate of the point of tangency, don't we just plug into the original function? So we would do a of -1, and that's going to give us 2 times -1 cubed minus 4 times -1 plus 5. That's 2 times -1, so -2, plus 4, plus 5. So that's giving 9, take away 2 is 7. So there you go. That's one part of the problem down. We know that the point of tangency is -1, 7. The next thing we would need to do is figure out the slope of this tangent line, because to find the point of intersection of the tangent line and the original graph, we would need to set their equations equal to each other. Now the equation of the big blue curve here is of course just the given function, this cubic, but we need the equation of the tangent line too, and to get that we first need our slope, and to get the slope we need the derivative. So this is where we have to do the limit definition of the derivative. Now there's two different limit definitions, of course. There's the one involving the limit as h approaches 0, and there's also the one where the limit is of x as x approaches some known x value. So if I did not know the value of x, I'd want to use the limit definition where h goes to 0, but I do know the x value that I want. I know that it's -1, so I would recommend that you use the other limit definition, the one where we let x approach the value of x where we want our derivative, and then you just do f of x minus f of -1 and divide that by x minus -1. So I'm going to use that formula to come up with the derivative, because the derivative will be the slope of the tangent line. So let's do that. So let me just copy this equation real quick because I'm feeling too lazy to write it down. But here it is. And I'll make myself some more room down here. And we'll do our derivative real quick. I'm hopeful that you guys can do this part already really easily by yourselves. But if not, here's another review, even though there's plenty of review materials out there already. So since I'm trying to find a prime at -1, I'm going to do the limit as x approaches -1. Of this whole function, so 2x cubed minus 4x plus 5. Then I'm going to subtract from that a of -1, which, okay, I can show the math here, but if you were paying attention a minute ago, then you know that we already did a of -1 up here when we were trying to find the y coordinate of our point of tangent C. So you should already know that that whole thing's going to come out to 7. And if you know that, if you get that, then there's no reason to show all that work again. You can just say, I know this is going to be 7. And then we're going to divide this whole thing by x minus -1. So we'll go ahead and just say x plus 1. But there we go. We're all set up. We're ready to go. This is going to now be the limit as x approaches -1 of a 2x cubed minus 4x. Is this right? Minus 2? Yeah, that's right. All over x plus 1. All right, and then something I didn't necessarily intend, but that's definitely happening here, is that we can't really factor the numerator. It's not a difference of cubes. It's not like a factorable quadratic. It's just kind of this weird cubic. But we know that if we were going to factor, then what we want to happen is we want one of our factors to be x plus 1, because we know that we want the x plus 1s to cancel. So really what we want to do is we just want to figure out who the other factor is if we factor out an x plus 1. And that's exactly what synthetic division is really good for, right? So why don't I go ahead and assume that x plus 1 is a factor of the numerator. In fact, I don't really have to assume it. I could plug in -1 and see what I get. But we do get 0. So we know that it is in fact a factor. So let's go do the math. So off to the side somewhere, I'll take my -1 and I'll divide it into the coefficients of this polynomial. First coefficient is 2, obviously. Less obviously, the next coefficient is 0, because remember you need a coefficient from every single power of x. So if you're missing a power of x, it's because the coefficient is 0. So that 0 is a placeholder for the x squared term. Then we'll go -4, then we'll go -2. Then the way this whole process works is you take this first number, just drop it down. Then you're multiplying. -1 times 2 is -2. Then you add, and you get -2. Then you multiply -1 by -2, getting +2, and you add, getting -2. Then you multiply again, getting +2, then you add, and there's that 0 that I told you we would get. And because we get 0, we know that x plus 1 really is a factor. But more importantly, we now know that the other factor is the polynomial with these coefficients. Now this guy on the end is always the constant, and then the powers of x go up, up, up from here. So it'll be -2, and then -2x's, and then plus 2x squareds, like that. So that's our other factor, and we can just slot that in here. So 2x squared minus 2x minus 2. And I don't really care that I can factor a 2 out of this. I don't care if it's factorable. I just want these guys to cancel, and then I can find my limit by plugging -1 into the only thing that's left. So I know that if you forgot what we're doing, by the way, we're still after our slope. And our slope is going to be a prime of 1. And we get that by just substituting in 1. So it's 2 times 1 squared minus 2 times 1 minus 2, which is 2 minus 2. Oh, that feels wrong again. I think I lost a sign somewhere. Hold on. Okay, found my mistake. This is obviously -1, my bad. So -1. So it's -1 squared, -1. So this is still 2, but this is now plus 2. And then minus 2. So that's giving 2. And that's our slope. Okay. So before you forget, don't forget, we also knew that our point of tangency was -1,7, which means we're ready to write the equation of this orange tangent line. And to write the equation of that orange tangent line, we'll just take our point of tangency, which was -1,7, and that for us is the x1, y1. And we'll take our slope being m, and we'll just substitute into the point slope form of a line, which was y minus y1 equals m times x minus x1. So now if we plug in our slope of 2, that goes right here. If we plug in the -1, 7, then we'll put 7 in for y1, we'll put -1 in for x, and then the rest is just algebra. So we go y minus equals this times x minus. And when we clean this up, we get y minus 7 equals 2x plus 2. Then we add 7 to get y equals 2x plus 9. Okay, it's been 10 minutes, so this obviously is kind of a long process, and we're not even done yet. But you should probably know that on the quiz, some of our questions will just stop right here, right? The only thing you have to do is write the equation of the tangent line, and we've done that. And you'll obviously do this a lot faster than I do if you're not chit-chatting on a video. So don't be too concerned with how long this takes. But also don't forget the fact that we just found that our slope was 2 and that the equation of this line was y equals 2x plus 9. We're still not done, because what we're actually trying to do is to try to find the other point of intersection of the line whose equation we just found and the curve whose equation we were given. This guy's 2x cubed minus 4x plus 5. And I said at the start of this problem that the way that you find the points of intersection of two graphs is by just setting their equations equal to each other and then solving. So that's literally what we'll do. We'll take this linear equation, set it equal to this cubic equation, and then solve the equation that we get as a result. So grab your 2x plus 9 and set it equal to your cubic, which was that guy. This guy. So 2x cubed minus 4x plus 5. And so this equation is now a polynomial equation, and the way that we solve those is to get them set equal to 0. So right away we want to subtract everything on the left from both sides. We'll let the left side go to 0. 2x cubed, we'll just bring that down. But then this minus 4x, we're going to subtract 2x from it, so we'll end up with negative 6x. And this plus 5, we're going to subtract 9 from it, so we'll get minus 4. Then you might notice that all of these coefficients are divisible by 2. So rather than having to factor out the 2, I can just divide by 2 since we're actually working with an equation. We're often not working with equations, we're working with just expressions, and then you can't divide things away, you have to factor them out. But in this equation, I can just divide both sides by 2, and of course I just still have 0. And all these coefficients get smaller. It becomes x cubed minus 3x minus 2. And unfortunately, you'll notice this is the exact same kind of cubic that when we were doing the derivative, we didn't really know how to take this cubic and factor it. So what did we do? We did synthetic division instead, right? So I'd recommend that again. We've got another cubic that's sort of not really factorable, but what do we know? We know that from this drawing we've already done, we know that one solution of the equation where the tangent line equals the curve, one solution is -1, right? That's definitely a solution because it's the point they share. So I could go ahead and start my synthetic division with the -1. So take the -1 that we know is going to work and divide it into the coefficients of this guy, which are 1 and again 0 and a -3 and a -2. And if you drop the 1 and multiply, you get -1, adding gives -1. Now you get +1, adding gives -2, multiplying gives +2, and adding gives 0, just like we knew it would. Which means I can begin to factor this cubic. One of my factors will be the x plus 1, and the other factor will be x squared minus x minus 2. And then that quadratic is factorable. So we now have an x plus 1, and this guy factors down to be an x and an x. Minus 2, we're going to go minus 2, we're going to go plus 1. And so notice there's two factors, that give us -1 as a solution. So we get -1 as a solution twice, and then we also get 2 as a solution. And that 2 is what's important to us, because again, if we go back to our little sketch, that 2 is telling us that our other point of intersection has an x coordinate of 2. Okay, that's what we just figured out. And we have to give the coordinates of the point, which means we do need the y value as well. And we've got choices here, because you'll notice this green point, it's on the tangent line, so we could plug 2 into the equation of the tangent line, and 2 times 2 is 4, plus 9 is 13. So this must be the point 2, 13. But I could have also plugged 2 into the original equation, because the green point also lies on the blue function. It's the point of intersection after all. So if I plug 2 in up here, I would get what? 2 times 8, which is 16. Take away 2 times 4, which is 8, plus an extra 5. That's 8 plus an extra 5. That's still 13. So notice that, at least for this problem, you could have plugged 2 into the tangent lines equation or into the original functions equation, and both would give the coordinates of that second point of intersection. So finally we're done with this problem. We're at 16 minutes and 16 seconds, but it wouldn't really take that long in real life. And also this problem contained literally everything you'd ever need to know how to do, right? Because in this problem we had to find the coordinates of the point of tangency. We had to use one of our limit definitions of the derivative to find our derivative. We had to set two equations equal each other and solve, and part of that solving involved synthetic division, so there's a lot to this problem. This is a good review for tomorrow for sure. Anyway, final answer? The final answer is the coordinates of the point of intersection, which we just said are 2, 13. So that's the final answer. All right, I hope that's helpful. Let's go on and try 2. And I'll try to go faster this time. But number 2 says, write the equation of the tangent line and the normal line to the graph of b of x, which is this quadratic. I think I liked the way it worked when I sketched it for you first to give you a better sense of what's going on, so I'm going to do that again. So what does this equation look like? Well, if I wanted to sketch this well, first thing I would do, hopefully, is factor out a 3x to be left with x minus 4. And then if you pay attention in Algebra 2, you know that 3x, one of its zeros, is 0. So we certainly have an x-intercept of 0. Then the x minus 4, his 0 is 4. So over here at 4 is my other x-intercept. And then the leading coefficient of this thing is positive. So I know I'm a parabola that opens up. And so this is no longer just kind of a rough sketch. This is a pretty decent sketch of this function now. And it says, write the equation of the tangent line and the normal at x equals 3. Well, if this was 0 and this was 4, then my vertex must be right at 2, which means the point of tangency we're talking about would be right here. And because I've sketched this pretty well, I can tell just by looking that the slope of my tangent line should be positive something. Now, I wouldn't trust the fact that it seems to be like positive 1, but it's definitely at least positive. Now, it's also asking for the normal line, and I'm sure there's a few people who still don't know what that means, but the normal is just the line that's perpendicular to the tangent line. So that would be this green guy here that comes running down. It goes through the same point of tangency, and it just has to be perpendicular to the tangent line, which means that they have to make a 90-degree angle. And what you should remember about perpendicular lines is, this is the symbol for perpendicular, by the way, the upside down T. But perpendicular lines have slopes that are opposite reciprocals. So again, what that means is, let's say for a moment that the blue guy's slope turned out to be, I don't know, positive 5/4, right? That's sort of close to 1. Then we know that the green guy's slope, the normal, his slope would have to be the opposite of this, so negative, and the reciprocal, so 4/5. Okay, so you're literally doing two things. You change the sign and you flip it upside down. But you would now have the slope for both the tangent line and the normal, then all you would need to do is find the coordinates of this point of tangent C, right? And that would be your x1, y1. Then to write these equations, you would plug into our point slope form, the y minus y1 equals m times x minus x1. So that's it. That's sort of the background information on this problem. Let's just do it now. And again, I would say that I think the first thing I'm doing is just trying to find the coordinates of this point of tangent C. We know that x is 3, so the y value at 3 would just be b of 3, whatever I get when I plug in. So I would get 3 times a 3 that is squared minus 12 times 3, which is 3 times 9, so 27. Take away 36 is negative 9. So okay, this picture's scale is a little off, but at 3, were you expecting a negative y value? Certainly should have been. We see that we're under the y-axis. So our point of tangency is the point 3 comma negative 9. That's a pretty good start at writing our equations. Now the next thing we need is the slope of the tangent line. You can't really get the slope of the normal line directly. You have to get it by first finding the slope of the tangent line, and of course to do that we use our limit definition of the derivative. So again, I'll grab this function and we'll use our limit definition to get the derivative at 3. And again, since I know that I just want the derivative at 3, I'm going to use my newer alternate limit definition, the one that instead of letting h go to 0, we're going to let x go to negative 3. So the derivative b prime when x is equal to 3 is going to be the limit as x approaches 3 of the original function 3x squared minus 12x minus b of 3, which again is what I get when I plug in 3. But didn't we do that math a second ago for the tangent line? The point of tangent C, which we decided had a y coordinate of negative 9. So again, rather than doing all that math again, let's just pull that minus 9 down and then divide this whole thing by x minus 3. And again, we'll simplify the numerator and we'll hope we can find an x minus 3 to cancel with the x minus 3 in our denominator, because then we'll be able to just evaluate by substitution. So we'll get the limit as x approaches 3. Upstairs we have a 3x squared minus 12x plus 9, which we can certainly factor a 3 out of. So now we'll just be doing the limit as x approaches 3 of 3 times 1x squared minus 4x plus 3 all over x minus 3. And then you should probably be noticing that that is factorable. So we're now looking at the limit as x approaches 3 of 3 times an x minus 3 times an x minus 1 all over an x minus 3. So that does get these x minus 3's to cancel, which means I can now evaluate this limit by just substituting in 3. So I'll get 3 times 3 minus 1, which is just 3 times 2, which is just 6. All right, and I know sometimes after we do these big long processes, you forget what the heck you even just found. So what is this 6? Oh, well that 6 is b prime of 3. What does that mean? It means it's our slope. Slope of what? Slope of the tangent line. And that means we can kind of kill two birds with one stone, because if that's the slope of the tangent line, then the slope of the normal must be the opposite reciprocal of this 6. So it would be negative 1 over 6. That means I now have the slope for the normal. I also have the slope for the tangent line. And don't forget, we already figured out our point of tangency too. Our point of tangency was 3 comma, I forget, negative 9, I'll go out on a limb and say. Yep, 3 comma negative 9. That means, if I were you, I just split my paper right down the middle, yoink. And over here, I'll go ahead and find my tangent line. And I'll find my tangent line by plugging in the -9 for y1. The slope of the tangent line is 6. And the x-coordinate is 3, so x minus 3. To find the normal, I'm going to do the exact same thing. We're going to go y minus, and we still use the same point of tangency, because the normal has to pass through that same point of tangency. So it'll be y minus -9. And the one thing that changes is your slope. We're going to use -1/6 this time instead. But again, we'll go x minus 3, because that's our point of tangency. So over here, when I go to clean this up, I get y plus 9 equals 6x minus 18. So if this is y plus 9, I'm going to subtract 9 from both sides. And I end up looking at y equals 6x minus 27. So that should be my tangent line. Then for my normal, I get a y plus 9. That equals -1/6 x plus 1/2. Then if I'm taking 9 away, I get y equals -1/6 x. If you take 9 away, you'll get -8.5. And of course, you know that I hate mixed numbers. So as an homage to me, you'll rewrite that. And you'll call it y equals -1/6 x. 16 plus 1 is 17, minus 17 halves. And then I hope those two answers make sense. We could always go back to our little drawing and find out. Looking here, it certainly looks like my tangent line should have a negative y-intercept. Oh, by the way, remember, these slopes were pretend. It turned out that the actual slope here was 6. And the actual slope down here was -1/6. But my tangent line was -6 minus 27. Again, is it feasible that this y-intercept down here is at -27? Sure it is. And it seems like my normal should be up here with a positive y-intercept. So what did we get? Oh, we did not get a positive y-intercept. Okay, that's fine. That just is because my picture was not drawn very well. This tangent line should actually be much, much steeper, which means my normal line would be much, much shallower. And it does make sense that I could have a negative y-intercept. So I'm trusting my answer. I think I did great. And we're done. Here's the equation of my tangent line. Here's the equation of my normal. So there. All right, let's try 3. 3 says, write the equation of the line that's tangent to the graph of this radical function and parallel to this equation. So, okay, what does that look like? I'm still definitely liking these sketches. So I'm going to draw myself a sketch. Now, sketching the radical function, I hope I don't leave anybody behind, but basically this is what? I'd flip this around, go -2x plus 6. I'd factor out a -2 and go -2x minus 3. And then seeing my function in this form, I know that 2 important things have happened. I've been translated 3 units to the right. Bing, bing, bing. So my endpoint's here. Then the negative coefficient on x means that my graph, which normally would kind of grow this way and look like the top half of a parabola, well, he's going to be reflected over the y-axis. So instead he's going to grow and go this away. But here now is a decent looking sketch of the function. And it says we're supposed to try to be parallel to the guy whose equation is -1/2x plus 5. Well, the 5 means I'm up 1, 2, 3, 4, 5. Maybe I'm here. And my slope is -1/2. So I'm coming down like maybe about like so. So that means the thing that I'm trying to write the equation of is the line that's parallel to this line, but tangent to the red function. So I'm going to draw this line right on top of it, and then I can grab it and drag it around. And we can see that if I kind of drag it down, maybe it's right here. Maybe there's my point of tangency. It's not sketched very well, but I bet my point of tangency maybe is here at like 1, or maybe here at like 2. Maybe it's 0. Hard to tell. But let's pretend it's here for sure. Then this blue guy is the guy we're trying to write the equation of. And there's one thing I know for sure already. That's that the green line I was given, he sure as heck has a slope of negative 1/2. Because his slope is just the coefficient of x, right? Isn't this thing mx plus b? So I know the slope of the green. And that means I know the slope of the blue, because when lines are parallel, they have the same slope. So this blue guy whose equation I'm trying to write, he definitely has a slope of negative 1/2. And that means I'm halfway done, because my equation is y minus y1 equals m times x minus x1. And we just said we know the slope already. So all we need now is the point of tangency. But like I just said, I don't really know where that is. So how do I get it? Well, if you go back to number 1 and 2, in number 1 we knew the x coordinate, right? And how did we find the slope when we knew the x? Well, when we knew the x, we used the derivative to get to the slope. Well, we do the same thing, right? If we know the x value, then we can find the slope. And same deal, if you know the slope, then you can go find the x coordinate. But it's a little different. Instead of plugging x into an equation, you're going to have to set your slope equation equal to your slope and then solve for x. I'll show you what that means. That makes more sense when I just do it. So what's our slope equation? Our slope equation is our derivative. So we definitely need to find c prime. And because we do not know the value of x, we can't use the limit definition as x approaches some known x value. The x value is unknown. So we're back to having to use the as h approaches 0 definition. And that's the one where we do c of x plus h, which would be 6 minus 2 times x plus h instead of just times x. Then we subtract from that the square root of 6 minus 2x. We're doing the original function now. And then we divide that whole thing by h. And you hopefully remember that because this numerator has 2 radicals in it, we'd want to multiply by the conjugate to get both radicals to cancel. So the conjugate would be 6 minus 2 times x plus h plus 6 minus 2x, square root of 6 minus 2x. And of course, whatever we do to the numerator, we must also do to the denominator. So I'll go 6 minus 2x plus h plus square root of 6 minus 2x. All right, now we've done this so many times that you should hopefully remember that what's about to happen is a lot of stuff in the numerator cancels out. So we'll be looking at the limit as h goes to 0. And when you multiply the first by the first, the radicals will cancel. So you'll just get 6 minus 2 times x plus h. When you do the outers, you'll get a positive product of the radicals. When you do the inners, you get a negative product of the radicals, and all that cancels. And when you do last times last, you get a negative this radical squared, so the radicals cancel, and you just get back the 6 minus 2x. Remember to put that in parentheses, or just remember to distribute the negative. But this will be all over, and here's where a lot of people go wrong. They go all over h, and that's it. But no, this h is getting multiplied by this whole conjugate. So our denominator actually becomes a big mess. Our denominator is h times the entire conjugate, which is 6 minus 2x plus h in parentheses under a radical plus 6 minus 2x under a radical, close parentheses. All right, I'm going to be a little lazy again, but upstairs we're looking at a 6 minus a 2x minus a 2h minus a 6 plus a 2x. And what usually happens again, where we see everything that doesn't have an h in it cancels out. The 6 cancels with the 6. The negative 2x cancels with the positive 2x. But we see we still have that negative 2h. So we bring that down. And that is now the only thing left in our numerator. This is still a limit, by the way. Don't forget to include your limit notation in every single line. Downstairs we have h times the conjugate, 6 minus 2x plus h, plus 6 minus 2x, close, yoink. All right, so now what? The h's cancel, boink, boink. And the second those h's cancel, we know that we can now plug in 0 to evaluate our limit. So plugging in 0 gives us a negative 2 over a 6 minus 2 times x plus 0 plus 6 minus 2x. And x plus 0 is just x, and 2 times x is just 2x. So we quickly see that we just have the same radical on the bottom twice, and that means we have a negative 2 divided by 2 square roots of 6 minus 2x. And a few people kind of left their answer like this on the last quiz, so just be careful not to do that. These 2's cancel, of course, and give a final answer of negative 1 over square root of 6 minus 2x. All right, and what's this thing again? It's the derivative. This is c prime. And why do we care that's the derivative? Well, we care because we know that the tangent line, this blue guy that we're trying to write the equation of, his slope is negative at half. And the derivative is the equation that gives those slopes. So if I grabbed this whole function, the negative 1 over 6 minus 2x, I would set that whole thing equal to negative 1/2. Because if I solve this equation now, that's going to tell me the x value where we get this slope. So to do that, you can either imagine cross multiplying, or you can imagine multiplying through by the LCD. I'm going to multiply by the LCD. So that's 2 times the square root of 6 minus 2x. And if I'm multiplying by the LCD, then that guy distributes onto the left-hand side, and he distributes onto the right-hand side. And when he distributes onto the left, the entire radical cancels, so you just get negative 1 times 2, which is negative 2. And on the right-hand side, the 2's cancel, but you get negative 1 times the radical, so you get negative square root of 6 minus 2x. Okay, and then from here, I notice both sides have a negative on it, so I might as well just divide both sides by negative 1, getting those negatives to cancel. Then it's pretty obvious I should square both sides next. So 2 squared goes to 4, and this radical squared, the radicals just cancel, and I get 6 minus 2x. And then I subtract 6, getting negative 2 equals negative 2x. Then I divide by negative 2, and I get 1. And, roll back the tape, but where did I say our point of tangency would be? Didn't I say my money was on it being 1? And we now know that it definitely is 1. So a decently sketched sketch can definitely really point you in the right direction. But where are we at? We're just trying to write the equation of that tangent line, right? And the way that we write equations of tangent lines is by plugging into y minus y1 equals m times x minus x1. And we already knew that m was a half because we had to be parallel to the other line whose slope was a half. After a whole bunch of work, we just figured out that the x coordinate of our point of tangency has to be 1. So the only thing we're missing now is the y coordinate, and that should be pretty easy. We just plug back into the original function, remember? So the original function, c of x, was the square root of 6 minus 2x. So if c of x was the square root of 6 minus 2x, then c of 1 will be the square root of 6 minus 2, aka square root of 4, aka 2. So we're basically done now. Once you have the slope and the point of tangency, the rest is just an algebra 1 problem. So we just now plug into our point slope formula and simplify a little bit to get the equation of our line. So you should be looking at a y minus 2, which equals 1/2 times x minus 1. which is a y that equals 1/2 x minus 1/2 plus an extra 2, which means y equals 1/2 x plus 1 and 1/2, aka 3/2. That's the final answer. We finally did it. We got to the equation of our tangent line. And again, just going back up to the top, yoink. We were trying to write the equation of this blue guy. And what did we just decide about him? The point of tangency was 1, 2. That feels pretty good. That looks like it's at 2. We just found that the y-intercept of our point was, 1.5? Oh, that feels bad if that's what we found. Uh-oh. Huh. Okay, I'm back again. Your boy Mr. F's a buffoon. I wrote down that our slope was 1/2 when obviously, because I made a nice looking sketch, we can see that our tangent line should have a negative slope. It's not positive 1/2, it's negative 1/2. And of course that's what threw off my y-intercept, so my bad. Please forgive me. This slope of course should have been negative 1/2, which means this would be negative 1/2, which means I distribute that in, getting negative 1/2 plus 1/2, and then 1/2 plus 2 would be 5/2 instead of 3/2. And then that makes a lot more sense because 5/2 is like 2.5. And we can see in our drawing that our y-intercept should be just a bit higher than this point. So this point being at 2, this point being 2.5, our slope being slightly negative. All that stuff feels good. I love that the equation of this tangent line is y equals negative 1/2 x plus 5/2. That is the final answer to that question. And I hope that made sense. And then comes 4. And I was working on 4 with another kid, and I really think that this doesn't end well. I think this ends with an equation that's pretty annoying to try to solve. I'm going to walk you through it anyway. Oops. I'm back. Let's do it. So what do we got? I'm going to go ahead and sketch it again. We were given a rational function. And a rational function like this, where it's just a constant over a linear, those are pretty easy to sketch because you can see that we have a vertical asymptote at negative 5. 1, 2, 3, 4, 5. And you can see that because the denominator has the greater degree, would have a horizontal asymptote at 0. And you can see that if you plugged in 0, you get positive 1/5. So we're above the asymptote. So we know we'll get one whole branch that's up above in this sort of quadrant, so to speak, and the other branch should be down here in the other quadrant. So there's a decent looking sketch of what d prime looks like. And then what are we trying to do? It says write the equations of both of the lines that are tangent and have slopes equal to negative 4. Well, negative 4 is pretty darn steep, so I'm thinking maybe it looks something like this. And this is another one of these problems where I know the slope, but I don't know the x coordinate where this happens. But my decently drawn sketch is making me think that maybe it's like negative 4 because my asymptote's at negative 5. Maybe negative 4 is giving me just the right slope. But it says there's a second line with the same slope. And yeah, I can eyeball that. Seems like that's probably right here. Boop. And pretend that hit like here. And again, if this guy's at negative 4, 1 unit left of the asymptote, then the other one's probably at negative 6, 1 unit right of the asymptote. Can we count on that kind of symmetry where if one is 1 unit to the left, the other is 1 unit to the right? I'm not sure. I'm not ready to say that that's true, but yes, I think that's true. Because that should feel a lot like odd symmetry to you, that sort of reflectional symmetry, reflect once, reflect again. So that is probably true. I'm not totally ready to say that it's definitely true all the time. But for functions as simple as a constant over a linear, I think it's safe. Anyway, this is the plan. So we need to be writing 2 equations again. You're supposed to be writing the equation of this first tangent line here, and also this one. So the good news is, notice, they both certainly have the same slope. and that slope is known to be -4. But they have different points of tangent C this time. This guy's tangent at this orange point of tangent C, and this one is tangent at this lavender point of tangent C. So somehow, some way, we got to figure out the x coordinate of this point of tangency. We think it's -4. We're not sure, but we got to find the x coordinate so that we can then plug in to find the y coordinate, and do the same over here. There'll be some other x and some other y. All right. So how do we do that? Well, we do it the same way we did it in the last problem. We know the slope. It's -4, and slope comes from the derivative. So if we can find the derivative equation and set it equal to -4, then we can solve, and we'll get our 2x values. Okay, so you probably should have expected this problem will involve finding the derivative, and of course it does. So 1 over x plus 5 is our function. All right, and again, we don't know the x value. We only know the slope. So to find d prime, we again have to use the first rule that we learned, the one where we're doing the limit as h goes to 0. And we'll do 1 over x plus h plus 5 minus 1 over x plus 5 all over h. And you guys have been doing pretty good at solving these. You guys mostly know that what we want to do is multiply by the LCD, the x plus 5 times x plus h plus 5. But if you want to multiply the numerator by that, you have to multiply the denominator by that too. And of course, if you multiply the numerator by this, then you have to distribute the whole thing onto that term, distribute the whole thing onto that term. And what happens when we multiply onto this first term? Well, this big trinomial is the one that cancels, and so we end up getting 1 times the smaller binomial, x plus 5. Then we subtract from that. When this distributes, this time the binomials cancel, so you get -1 times the trinomial, x plus h plus 5. And everything in the denominator canceled, so we're back to just a regular fraction. And in the denominator, again, resist that urge to just say this is h. It's not just h, it's h times this entire LCD. So it's h times an x plus 5 times an x plus h plus 5. All right, but again, we're doing the limit as h approaches 0. Which means these two h's are really cramping our style. Actually, just this h. This guy too, I suppose. But we know that that h in the denominator, if we tried to plug in 0, would give us division by 0, would be undefined, and that's not good. So we do what we always do. We simplify our numerator, where distributing 1 just gives x plus 5. I just don't need the parentheses anymore. Then distributing the -1 gives us minus x minus h minus 5. And then we can start canceling like wild. So the x cancels the positive x. The positive 5 cancels the -5. But I still have a negative h, but we know that even that negative h cancels now with that h. So now the only thing left in the numerator is this little factor of -1. So we have -1 over x plus 5, x plus h plus 5. And by the way, we're going to let h be 0. So this is actually x plus 0 plus 5, which is, of course, just x plus 5. So really what we have is -1 over x plus 5 squared. And that's the formula for our derivative. So this is d prime. So this formula is all good. If we knew a value of x and we wanted to find the slope, we'd plug in our value of x and would calculate. But that is not what we know. Remember, what we know is that we want to know when the slope is 4. So we know the slope and we want to solve for x. So that again is when we take the whole derivative equation, and instead of plugging into the equation, we set the whole equation equal to the slope that we want. which is negative 4. Then we have to solve. And again, you could just throw this over 1 and just imagine cross multiplication. But really what you're doing is multiplying by the LCD. So that's an x plus 5 squared, distributing onto both sides of this equation. So he distributes over here and just cancels out, leaving us with negative 1 on the left. Then it distributes here, nothing cancels, so you get negative 4 times x plus 5 squared. Oh, okay. You know what? I feel silly now. Because when I went to solve this with the other student I was working with, I took this and I expanded. Again, what I'm about to do is wrong. Don't listen to me. I'm going to expand this, getting x squared plus 10x plus 25 times a negative 4. I distributed the negative 4 onto that. That gave me negative 4x squared plus minus 40 minus 100. And then because I want this to equal 0, I would add 1 to both sides. So I got minus 99. Yeah. And then you just had this big nasty quadratic that like you couldn't really factor. I mean, maybe you can, but the numbers are big and ugly and nothing cancels out and it's gross. So just don't do that, because in the form that we're in already, where we're light blue, you can just divide both sides by negative 4, getting positive 1/4. Divide by negative 4, divide by negative 4. Those cancel, and over here you get positive 1/4. And that is equal to x plus 5 squared. So you can just take the square root now of both sides. And the big thing to remember is when you take the square root, you're going to get a positive root and a negative root. But the square root of 1/4 is 1/2. But remember, it would be plus 1/2 or minus 1/2. But that now just equals x plus 5. So our two solutions are what we get when we let x equal positive 1/2 plus, minus 5. So it'll be the positive 1/2 minus 5. And our other solution will be negative 1/2 minus 5. Ay, chihuahua. All right, negative 1/2 minus 5. There, I wrote it correctly now. So that means this is negative 4.5, aka negative 9/2. And this would be negative 5.5, aka negative 11/2. So those are our x coordinates. And I guess we can't stop there. We have to write the actual equations. So this is still kind of nasty. I'm just going to say let's not even continue from here. If these numbers were nicer, then you would do what we've done 100 times before. You would take the negative 9/2, you'd plug it into the original function to find its y value, and then you could use that point of tangency with our slope, which was negative 4, to plug in and write the equation of that tangent line. Then you'd do the same with the negative 11/2. You'd plug that into the function to find its y value, use the same slope of negative 4, and you can get it. But even from here, I don't think I want to do this, just because plugging in negative 9/2 would be what? That would give 1 over negative 9. You know what? It's not that bad, but you guys don't want to hear me. But I'll keep going for the people that do. Since it's not that bad, we'll go negative 9/2 plus 5. And just remember that 9/2 was, what, 1/2 less than 5? So adding 5 back onto this just gives you 1/2. And 1 over 1/2 is 2. Which again, I hope makes sense, because at this point we're just saying that y value is 2, which I guess it is. So, bringing that number down, when we plugged in the negative 9/2, we got an output of positive 2. So we could write our equation, and our equation would be y minus 2 equals negative 4 times x plus 9/2, which means y is equal to negative 4x plus 36 chopped in half is 18. But it's not plus, it's minus 18. And then, of course, the minus 2 from over here, I'm going to add it back over. So I'm adding 2. So I'm getting an equation of negative 4x minus 16. Does that negative y-intercept feel good? Yes, it does, because we're getting negative 16. Now the other y-intercept we should expect to be a bunch lower. So let's do that too, I guess, if anyone cares. But we're halfway done. This is one of our tangent lines. The other tangent line would still use the slope of negative 4. Its point of tangency would use the negative 11 halves, which if I plug into the original function, which was, remember, just 1 over x plus 5, then that'll be 1 over negative 11 halves plus 5, which is really just 1/2 less than 5. So if you add on 5, you'll get negative a half. So you get 1 over negative 1/2, which is just negative 2. So again, that y coordinate came out pretty cleanly. And now I can substitute in, getting y plus 2 equals negative 4 times x plus 11 halves, which is going to be a y that equals negative 4x minus 44 halves, so 22. Take away an extra 2, so we actually get y equals negative 4x minus 24. So that's what I'm getting. It has been almost an hour to do 4 problems, but yeah, that's kind of right for problems like this. These were long and involved. The quiz will not involve problems that are quite this long and involved. Maybe there'll be one, but I'll ask some other shorter, more manageable questions. But that's it. So hopefully all that made sense. If it didn't make sense, then make sure to see me tomorrow. Not during advisory because we don't have advisory, but see me at lunch or after school. Yeah, and leave comments. If you have a question, leave a comment. I'll try to check it and give you an answer. All right, anyway, have a great night. Bye.